Okay, so taking a look at the periodic table and how atoms are set up, this is the chapter where we take a look at what scientists and what the ideas were that led to our current theory of the atom. Early atomic models was Aristotle, just said that things are made out of the four earthly elements: earth, wind, fire, water, that kind of thing. And Democritus actually coined the term atomos, meaning indivisible. We know now that that's not true, but at least he came up with the idea that it wasn't those primal elements. There was something else. John Dalton actually came by and later proved, using mathematics and science rather than just philosophy, he proved that basically the foundation of our atom theory, that all elements are composed of indivisible atoms. We know that's not true. We can split it now. But at the time, they didn't have the technology to split the atom. It doesn't happen naturally within our known area anyway. Um, every element is different in that it has a different type of atom. Flashing forward to what we know now, why they're different is because of the different number of protons and electrons. Number of neutrons can be the same, but definitely the different elements are made out of different atoms due to the number of protons and electrons. Whole number combinations for forming compounds. That's nice. It makes our job a lot easier when we have H2O rather than H2.17, O1.079, something like that. It's nice whole number ratios, and that allows for compounds to be formed. And really, when we have a chemical reaction take place, we're just splitting up the combination of things and rearranging them into different compounds. We never really change or alter the atom itself, they just move around. Electrons themselves were discovered by Thomson, and Thomson was basically just one that proved that electrons were there. These atoms were not just simply like Legos. They actually had parts to them that had different behaviors. And as the diagram shows in the cathode ray tube, these rays, these negative rays, just from electricity going through, were actually attracted to a positive pole. They bent up. So he said that we have a plum pudding model. In our terms, it'd be more like probably something like a blueberry muffin, where the muffin would be this big nebulous positive charge, and the blueberries would be these negative charges scattered throughout. They improved on that, and they found that protons and neutrons must be there. Make sure you use your book, page 110, that talks about the reasons why, but essentially, the math didn't add up. These electrons really didn't have any mass, but there are other problems with it for why this concept wouldn't work. Goldstein did observe particles going the opposite way. Basically, he replicated Thomson's work, and he saw there was actually a back ray that was going. The forward ray was going to be the electrons, a cathode ray, but he did observe in a different set of environments that there was a back ray, and he called those protons. So now protons exist, and the question is, okay, what does that look like? The diagram that just came up that philosophy didn't come up yet. They didn't really know this. But we did find some inconsistencies, and the problem is electrons essentially have no mass. So where's the mass of all this thing coming if it's just protons and electrons? Well, Chadwick discovered that the rest of it is actually a neutrally charged particle, and he called it the neutron. We didn't know where it lived. We didn't know where all these subatomic particles lived, and that was due to Rutherford's gold foil experiment that actually revolutionized. Okay, so he passed this through, and he was able to plot a nucleus, and this nucleus had a positive charge. That means that the rest is what we currently think, that the atom is mostly empty, a void, a vacuum. There are electrons scattered outside of this nucleus, but in the nucleus is the protons and neutrons. Okay, so we flash forward to like a Niels Bohr type of model that you just saw. Now, Millikan actually discovered a little bit more about the electron and essentially proved that it had no mass and that it had, compared to other particles, it had a one particle unit of negative charge. So for every electron we have a negative one charge, and for every proton we have a positive one. Okay, so today's model we know that the electrons don't sit on a path like the Bohr model, but more so that they're vibrating in and out. They're statistically everywhere, but what you see in the dark regions is more likely where they're going to be at any given time. So we do see some paths, and they aren't simply like a Bohr model is kind of a planetary model, how the moon will be locked in an orbit around, and we would know precisely where it is at all times. Today's model isn't that easy. It's more of an electron cloud where we see them scattered. Now, from all of this, what makes an element different, what makes an atom different, is the number of protons. So on a periodic table, we see an atomic number. That number tells us the number of protons. Since the atoms are electrically neutral, it infers that the number of electrons balance or equal the number of protons. An element's mass, okay, what gives the element mass is the number of protons and neutrons. So if we know the element's number and we know the element's mass, well, the number is the number of protons, remember. We know that protons plus neutrons is going to be the mass number. Well, we can figure out the number of neutrons. We simply subtract off my protons, and I'm left with just neutrons. Let's take a look at an example of that. Okay, I'll erase my chicken scratches here. And, okay, neon. Element number 10. Okay, so that means that I've got 10 protons, and essentially it means that we have 10 electrons, if it's electrically neutral. Now, its mass number is 20, so that means that I have 20 protons and neutrons here. Okay, well, wait a minute. I've got 10 protons. I already know that I've got 10 taken away, or 10 accounted for, so that means I have 10 neutrons total. If we look at beryllium, okay, beryllium, I have 4 protons. Well, its mass is 9, so 9 take away 4, the number of neutrons and protons is 9. Well, 9 take away 4, because I already know I have 4 protons, that means I have 5 neutrons. And the atomic number on sodium is 11. That means I have 11 protons, 11 electrons. Electrons essentially have no mass, so we don't worry about that. I subtract the mass number from the atomic number from the mass number. I end up with 12. That means I have 12 neutrons. Now, that's it looking at a balanced, just a whole number for its mass. If you look on a periodic table, sodium, in fact, does not have simply a 23. In fact, its atomic mass on the periodic table, on some of them, is listed as 22.990. How does that work? Well, the reason is because we have isotopes. They're different flavors of the same element. Take, for example, carbon-12. There are carbon itself. There are 3 forms of carbon that we know of: carbon-12, carbon-13, and carbon-14. By far and large, we have more carbon-12 than anything else. What makes these atoms different from one another? They're still carbon. They all have atomic number 6, which means that we have 6 protons in each of them. This is, when we list it as carbon-12, we're referring to its mass number. So this first version of carbon, carbon-12, means that I have 6 neutrons. 12 take away 6 protons, leaves me 6 neutrons. This version of carbon is carbon-13. I know it's carbon, so I already have 6 protons taken care of. That means I have 7 neutrons. So this is a flavor of carbon that has 7 neutrons. And the last one, the most famous one, because we use it for carbon-14 dating, for gauging the age of fossils and so on, tells us how old the Earth is. This is carbon-14. Okay, 6 take away 14, or 14 take away 6, excuse me, is 8 neutrons. Okay, so it's just different flavors of the same element. And we see lots of different examples there. Now, how do we get different masses? If I was to take the average, if we had these 3 different isotopes in equal amounts, my average would be 13. But in fact, on the periodic table, you'll see carbon listed as 12.011. The average atomic mass is 12.011. That's because I have way more carbon-12 than I do anything else. So let's look at an example of how we figure out calculating the average atomic mass when we consider in isotopes. All right, here's what the problem would look like. Okay, the average atomic mass of silicon, we know that we have 3 forms. We have silicon-28, I have silicon 29, and I have silicon 30. Okay, if I was doing a straight average, the average is 29, and I just write 29 on my paper. But I have 90% of this is silicon 28. 8% is this, and 2%, a mere 2%, is silicon 30. So what I do is I multiply 90% times 28. In other words, I'm going to rewrite this, 0.90 times 28. I'm going to add that to 8%, 0.08, be careful, it's not 80%, it's 0.8, 29, and I'm going to add that to 0.02 times 30. Now remember, the average atomic mass, if I just did a straight average, would be 29. Add them up, divide by 3, I get 29. If I do this, this ends up being 25.2 plus 2.32 plus 0.6. Oh, it's amazing I can do this problem in my head so fast. I add that all up, I end up with 28.2 is my average atomic mass, nowhere near 29. And that makes sense because 90% of silicon is this form. Only 2% is this. So my average is going to be a lot closer to 28 than it is going to be to 29 or 30. That's how we do average atomic mass. Okay, and basically this just says everything is based around carbon 12. And so when we look at our masses, it's not 12 grams. It's what we call a 12 atomic mass units. Okay, it's not grams at all. We'll get to this this number here later on in chemistry. It's Avogadro's number where we can actually convert that into grams, but we're not going to worry about that. Okay, it's all relative to that. So hydrogen would be 1/12 of the particles because there's 6 protons and 6 neutrons. So it's just listed as atomic mass 1. Okay. Along comes Mendeleev. He looks at all these problems, all these elements, all these atoms, and he says, okay, let's get these organized. So he comes up with a periodic table, repeating traits, and he noticed that all of these things, these elements, had similar types of reactions. They behaved similarly. So he repeated them. I'm going to flash forward to a periodic table in a second here so you can see it. And how Mendeleev had set it up is he noticed that he organized them in order of increasing atomic mass. Moseley, about 100 years later, said, well, I noticed a couple of inconsistencies. We should actually move this to atomic number, not atomic mass, but the number of protons that they have. That's what gives it its characteristics. Okay, so just a slight difference between them, and now we have the periodic law. Elements are arranged in order of increasing atomic number, and these traits will repeat, and that's what we call the periodic table. Okay, so let's take a look at just what this might be. And I'll just pull up a periodic table for you, and then we can be done. If this will come up. There we go. Okay, so just looking at a periodic table, let's label up a couple of parts here so you can see them. All right, so here's your periodic table. These are periods. Period 1, 2, 3, and they've listed them here. Periods means rows, not columns. Okay, there are 7 total periods, and you might look at these guys and say, well, wait a minute. These guys, you see this little asterisk here, belong right there. Okay, it starts with lanthanum, ends with ytterbium, and lutetium is the beginning. Basically, this 57 through 70 sticks straight out at us. We've got a thing pop-up book here. Now, the actinoids, they belong right here, 88, and then it goes 89 to 102 with nobelium. And then 103 back down to lawrencium. So those 2 green columns, the lanthanoids and actinoids, they have their own traits. They act similarly, and they pop straight out at us. So we have our periods here, our repeating traits, 1 through 7. This group right here is called the alkali metals. That's group 1. Group 2 is the alkali earth metals. Columns 3 through 12, okay, these are called the metalloids. Okay, we don't really worry about 13, 14, 15. Okay, these are going to be our non-metals. I guess that's what we could just say here. These are our non-metals here, but this column number 18. These are our noble gases. They don't really have much to do with one another. Here's our halogens. And one that I always add in is the chalcogens. That's column 16. Okay? Now, if we look on the periodic table, we'll also see most of them. This one doesn't have it, but you'll see this. It's a little step ladder. Okay? And those are, actually, I mislabeled this. These are not metalloids at all. These are our transition metals. Got ahead of myself in my thinking. These are my metalloids. And what that means is they have properties of both my metals and my nonmetals. Okay? So we skip boron. Okay? Or we start with boron. We skip aluminum. We know aluminum's a metal. So here with boron, that is a metalloid. It has properties of both. Then we skip aluminum and we go down and over. So we start here. We skip this guy. We go over to silicon. Germanium, astatine. All of these are what we call metalloids. All the ones that this staircase actually touched. Where's my staircase in all this mess? Right here. I call it a down and over rule, where we start with boron, we skip aluminum, we have silicon, germanium, astatine, and so on. We keep on going down the line. Those elements that this staircase touches, those are my metalloids. Okay, so pretty straightforward. Just make sure you look at a periodic table and see those. All right. So what does it mean to be a metal? Well, there we go. We see those things. Remember, ductile means you can draw it out. Malleable means that you can hammer it into sheets. And lustrous, well, you know what luster is. It's kind of a shininess to them. Okay, so those are our transition metals. All of those are metals. Chalcogens are and all of these nonmetals are poor conductors. They're non-lustrous. They're kind of just not much to look at. They're very brittle solids and gases. They're liquids at room temperature, various states. And we saw where the lanthanoids and actinoids were. Okay, down and over rule, we skip aluminum. They have traits of both metals and nonmetals. And there you have the entire chapter. Everything you need to know about the basic development of the atom and the periodic table and how it is set up today.